Hello class, this is my third video that relates to calculations with heating curves. So far in my first video we saw an introduction to the vocabulary, we saw an introduction into your heating curve. In my second video we identified our equations and determined the location of where we use those equations and those constants on my heating curve. Now in this third part video we're going to actually hit some calculations, go through the steps that we need to follow, and do some math. Alright, the steps that we're going to follow when we calculate. First things first, figure out what situation is being described, where that shows up on the heating curve. Are you warming or are you freezing? Are you changing your temperature or are you staying at the same temperature, just changing your phase? You need to read context clues, you need to determine what your question is asking you and where that shows up on the heating curve. That is the very first step. From there, your next step is to figure out what equation matches that location on your heating curve. We've talked a little bit about your units, so your unit for specific heat capacity being joules per gram degree Celsius. Well, sometimes it won't give you grams, it might give you pounds. Often joules, because they're so small, it'll give you values for kilojoules. So depending on what you have for your specific heat capacity, you might need to convert some of your units so that we can cancel these units once we have them in the mathematical equation. So your first or your third step, you might need to convert your units into heat should be in joules, and your mass has to be in grams so that they can cancel this unit in your heat capacity. Fourth, and it comes in a later video, but you might need to change and manipulate your equation in order to isolate what you want to find. For example, we've seen the equation Q is equal to MC delta T. That's nice and dandy and all if you're finding Q, but what if you're finding mass? How to manipulate equations come in a later video, but if you need to, it would come in step 4. And then your last equation, or the last step that we're going to solve, the last step we're going to follow is to take the values that you're given from your problem, plug them into your equation, and then solve for your variable that you're trying to find. Okay, those are the steps. Now let's get some examples. First, a cup of hot coffee, 100 grams, cools from 80 degrees Celsius down to comfortable room temperature of 20 degrees Celsius. How much heat is involved? So step 1, we need to draw ourselves a heating curve. So I'm going to do my 5 regions, slant, flat, slant, flat, slant. This is my temperature. This is my energy. This flat line is at 0 degrees Celsius, and this flat line up here is at 100 degrees Celsius. There is my heating curve. I need to figure out where I am. What location am I on this heating curve? Am I solid? Am I melting? Am I liquid? Am I boiling? Am I gas? Am I freezing? Am I condensing? It all depends where we are. So we've got hot coffee, 100 grams. It's cooling from 80 degrees Celsius down to 20 degrees Celsius. So I'm starting at 80, I'm ending at 20. Well, here's 0, here's 100. Both of my numbers are between 0 and 100. So I'm going to start right about here-ish. I'm going to call that 80. I'm slightly less than 100 degrees. And I'm ending at 20, so I'm going to end somewhere here-ish, above 0 degrees, and I'm coming from there and ending there. I drew my arrow to show that I am cooling down, not heating up. I'm going from right to left, cooling down my substance, getting rid of energy, not heating it up and adding energy. All right, our next step is to write down the equation. Well, here I'm a liquid. So and I'm in my middle region of my heating curve. So if I come over to my heating curve in my liquid phase between 0 and 100 degrees, I'm going to use my Q is equal to MC delta T equation. So Q is equal to MC delta T. And keep in mind, this C is for my liquid phase. Well, I'm already given grams, so I don't have to change that unit at all. I can just, and I'm trying to find heat, so I can use the equation as written, so I can skip steps 3 and 4 and move right into my plugging in the values and then solving. So I've got a cup of hot coffee, 100 grams. That goes in for my mass. Because it's grams, it's the amount of substance that I have. It cools from 80 to comfortable room temperature, which is 20. Those are the temperatures I'm given, so that's going to help me find my final temperature. Something to keep in mind is that your temperature change is your final minus your initial. So whatever you end on minus what you started with. I ended on 20 degrees Celsius. So I'm going to put in my 20 degrees Celsius minus my 80 degrees Celsius. I've got my M, I've got my temperature change. Now I need to put in my C value. This is the C of a liquid. Well, if I look on my reference sheet, you will be given all those values. You'll be given all those constants. I did write them here on my heating curve. My C for liquid water is 4.18 joules per gram degree Celsius. That is the constant for just liquid water, so that's the number I'm going to plug in here. Joules per gram degree Celsius. Before I go further, let me just double check that all my units cancel. Right here I'm in grams, and here I've got grams on the bottom, so my grams would cancel. Here I've got degrees Celsius, and here I've got degrees Celsius, so that would cancel. Nothing else cancels. I'd be left with joules, which is a good thing because I'm trying to find heat, and heat is measured in joules. All right, now what I have to do is start plugging this in my calculator and solving. I'm going to do the subtraction part first. So 20 minus 80 gives me a negative 60 as my temperature change. Then from there, I need to take my mass times my C times my temperature change. Anytime you have your values right next to each other, it means that you're being multiplied together. So 100 times 4.18 times my negative 60 equals Q of negative 25080. My unit I said was joules because it didn't cancel out. Now, what does this negative mean? How can I have a negative amount of heat? This negative number is referring to my heat being released from my system. So it's coming out of my system, this being an exothermic process. Because heat is released, I'm getting rid of my heat in my substance in order for it to cool down. And that's my answer. Let's try a second example. A 15-gram sample of ice warms from negative 10 degrees Celsius to 0 degrees Celsius. How much heat is involved? Again, I'm going to start by drawing my heating curve. And labeling my location on that. So I've got a 15-gram sample of ice. Already you should be thinking, okay, this is a solid. I'm warming up, so I'm going to have a temperature change. Going negative 10 to 0. All right, well, my 0 is where my flat line is. I'm a negative value, so I'm going to be less than 0. I'm going to start way down here at negative 10. And I'm warming it up to 0 degrees. Now, it hasn't said anything about melting. It hasn't said anything about going higher than 0 degrees. So I'm going to assume that I'm ending here when I'm a solid at 0 degrees. So I'm in this region, and I'm warming, so I'm going that direction. Next step is to figure out what equation goes along with that part of our curve. So if I look back to my heating curve, I'm going through a temperature change. So I'm going to use my Q is equal to MC delta T. Because I've got this slant, I've got a temperature change. Hey, that's the equation I just used in my example 1. But what's the difference? Well, it's because I'm not a liquid in this region. I'm instead a solid. So we're going to have a different number for our C value. But otherwise, the rest of this calculation is going to be similar to our example 1. My heat is what I'm trying to find, how much heat. A 15-gram sample, that's going to be my mass. Tells me how much of my substance I have. Let me write it like this instead of parentheses. It's warming from -10 to 0. So I've got my temperature change, final minus initial. Well, my final is 0, because that's where I'm ending, minus my initial amount where I started, which was a -10. Anytime you have this double negative, so a minus and then a -10, they end up being positive signs. So this ultimately has a temperature change of positive 10 degrees. And that's a temperature change, mind you. I'm still have to multiply it by my other values in here. So, C of my solid, look on my reference page. It gives me 2.1 joules per gram degrees Celsius as my C of a solid. Plug this into my calculator. I've got 15 times 2.1 times my temperature change, which was 10 degrees, and I get a whopping 315 joules for this amount of heat. Moving right along to a few more examples. Example 3. A 15-gram sample of ice at 0 degrees Celsius sits on the counter and melts. How much energy is involved? Okay, step 1, we need to draw our heating curve and determine our location on our heating curve. I am ice at 0 degrees Celsius. Okay, well here's my 0 degrees Celsius part. I'm somewhere along this line, either on this side or on this side. Well, let's figure out which side, because I'm not in both, and there is a correct answer to this. Notice it says ice at 0 degrees Celsius. It doesn't say liquid at 0 degrees Celsius. So because of that ice component, I'm not only at 0 degrees Celsius, but I'm also along, I'm here by where I'm a solid. If it had said a liquid at 0 degrees Celsius, I would have been way over here, because this is your liquid line. And at this point, that would be where I'm a liquid at 0 degrees Celsius. Told me ice, so I know I'm a solid at 0, so I'm going to start on this left side of my line. It sits on the counter and melts. Okay, my melting process is along this line. It doesn't say anything about heating it up after it melts. It doesn't give me anything about temperature changes. It just says I'm ice at 0. So I'm moving along this flat line from left to right because I'm melting. Well, my equation for going from a solid into a liquid is my Q equals MHF. because again, HF is defined as the amount of heat needed to melt a solid. When you're melting solids, you're using the equation that has HF. Also, when you're freezing, you're using that same equation. I don't have to convert units. I don't have to manipulate this around. We're just focusing on calculating heat. So now I can plug in the values that I know. I've got 15 grams. That's going to go in for mass. My value for water, for HF, if I look on my information sheet, it's 334 joules per gram. Let's double check to make sure my units cancel. For example, here's grams on top, here's grams on the bottom. Those would cancel. I'm left with joules. Good, because I'm trying to find heat, and heat has a unit of joules. And then from there, I simply plug this into my calculator. So 15 times 334 equals, Q is 5010. Be sure to include your unit, which we said earlier was joules. Much easier equation to look at and to use because we're not going through temperature changes. That's because we're not speeding up our particles. We're instead pulling them apart. We're changing their phase. We're changing their arrangement. We're melting them. So we're this flat line without any temperature change. Okay, our last example. A 35-gram sample of water is placed on a hot plate and is heated until it turns into a vapor at 100 degrees Celsius. How much energy is involved? Again, step one, I need to sketch out my heating curve. Figure out my location on that heating curve. A 35-gram sample of water placed on a hot plate is heated. Okay, so I'm heating this substance, meaning that I'm changing my temperature. It turns into a vapor at 100 degrees Celsius. Okay, when I wrote this question, I forgot to include an initial temperature. We're water, so we're a liquid. We know we're starting somewhere in this line. We're heating it, so we're going to go through a temperature change. It's turning into a vapor at 100 degrees Celsius. Okay, well, here's my 100 degrees Celsius line. This location would be if I'm a liquid at 100 degrees Celsius, but it does say I'm a vapor at 100 degrees Celsius. So I'm going to end way over here. So I have to heat it up, and then I have to boil it. Now, this was my error that I did not give you an initial temperature. You would normally be given an initial temperature. If I had been writing this when I have full brain capacity, I would have written this correctly. So my apologies that there is that mistake in there. Let's add it into the problem. A 35-gram sample of water at 50 degrees is placed on a hot plate and is heated until it turns into a vapor. All right, so now we're still here and here, starting at 50 degrees, heating it up. That's going to be this process here. And then I'm turning it into a vapor, so my evaporation process at 100 degrees is moving along this line. Now, this is a multiple step process. I'm in two different regions of my curve. I have to take that into account when I'm calculating my heat. So let's call this one step, and this is going to be my second step. For this first region, when I'm heating up my substance, well, I'm water. It doesn't say anything about ice, so I'm a liquid. When I'm changing my temperature and I'm a liquid, I'm going through this process here. That's my Q is equal to MC delta T equation. So for this middle region where I'm a liquid heating, I have Q is equal to MC delta T. where my C is a liquid. Now, for the second process, I'm going from a liquid into a vapor, so I am vaporizing this, I'm boiling it, I'm evaporating it, whichever term you want to use means the same thing, going from a liquid to a gas. I have a different equation. There's no temperature change, so I can't use this equation. Because I'm going from a liquid into a gas, I need to be using my Q is equal to mHV equation, the process to vaporize this. So those are my two equations that I will be using. I don't have to convert my units because I'm in grams and it gives me Celsius. So let's just start plugging in what I know. My Q is what I'm trying to find. My mass is 35 grams. My C for a liquid, if I look on my reference sheet, it tells me that the heat capacity of a liquid is 2.1 joules per gram degree Celsius. And then my temperature change, again that's final minus initial. So I'm ending, my final temperature is way up here at 100. Now, let me pause for a moment. This equation is only for this region. So I have to look at the temperature change of this region. Well, this region only goes to 100 degrees. So I have to use that as my final temperature. Let me go on a little side tangent right quick. If we had ended way up here at like 150 degrees, just theoretically, this equation is only for a liquid, only for this region. So even if I end at a higher temperature, I can only use this maximum number as my final temperature. I would have to use a different equation to do this region of my curve. All right, thank you for my little side tangent. Let's cross that out because we're not going that far. All right, final temperature is 100 degrees. That's where I'm ending. Initial temperature where I started is 50 degrees. So I'm going to do final minus initial. Well, 100 minus 50, that's a temperature change of 50 degrees. When I plug this equation into my calculator, I get 35 times 2.1 times 50 equals 3,675 joules of energy. That's only the amount of heat it takes to heat my liquid water from 50 to 100. I haven't taken into account the amount of energy it takes to pull my particles further apart. That's where this equation shows up. So Q is equal to, again, I still have the same mass. I didn't get rid of any of my particles. So 35 grams. And I'm multiplying that by the energy of vaporization, heat of vaporization, to pull my particles apart, which is, if I look on my constant sheet, it's 2,260 joules per gram. Plug that part into my calculator. 35 times 2,260 equals, this amount of Q is 7,900. My grams cancel because this is on the top, this is on the bottom. I'm left with units of joules. Okay, so I've got two numbers for heat. This first one for this region of my curve. This second one for this flat region, my boiling process of my curve. Now what do? Well, I need total energy, so I'm going to add these two numbers together so I can get total energy. So 3,675 plus my 7,900 number equals, I get a total energy of 82775 joules. And that is my final answer. That's all the example problems I have. I hope that was helpful. Come see me if you're still having difficulty in picking out equations, picking out constants. Please come in and see me. Let me know if you're struggling. I don't know how to help you if I don't know what you need help with. Hope that was helpful. Have a great rest of your day.